good. All right. So apparently somebody changed the battery of the school, mic, so I can use a little bit of amplification today. Um, the video is already getting streamed, so that's good. We definitely got audio here. So I'm going to close this, minimize, and we'll move on to class content. This is the previous class on the 13th, and the last topic that we were discussing had to do with comparison, and that's what the lab was how to compare binary numbers. And you probably remember, hopefully you do, that there are several things for comparing. The first thing is the borrow flag is useful to indicate whether a minuend is less than the subtrahend, but for what type of interpretation? How do we interpret the bits if we're using the borrow flag? It'll be unsigned. Very good. Okay, so if you look at a binary number using the unsigned interpretation, then the borrow bit is all you need to understand to know whether a minuend is less than the subtrahend or not. What about the sign flag by itself? Is it useful? Just by itself. If it is useful, is it like universally useful, or there are times that you cannot rely on just the sign flag? There are exceptions because in a subtraction, the result can be out of the range that you can actually store. So in that case, which flag do you have to kind of rely? What is the second flag that we had to compute in order to check whether the sign flag can be trusted? No, not carry. Carry is for addition. The overflow, okay, the overflow flag that I use an uppercase O to represent it. So the overflow flag takes a look at the sign bits of the minuend, the subtrahend, and also the difference in order to determine whether the sign flag may be erroneous or not. Do you guys remember that? Sort of, maybe? Okay. So when we combine the sign flag and the overflow flag using an exclusive OR operator, what do I call that flag in this class? Which letter did I use? The L flag. L stands for less than. Okay, so the L flag is, so if the borrow flag is useful for a certain interpretation of the bits, what do you think the L flag is useful for? There are two interpretations, or two ways to interpret bit patterns when we are only dealing with integers. So the borrow flag deals with the unsigned interpretation. The L flag is going to be useful for the signed interpretation. Very good. Okay. So that's where we stopped last week. So this is just a, quote unquote, previously, just to bring you up to date to, where we are in this class. So is that okay? All right, cool. And, what you see on the projector is basically just the class recording from last Thursday. So we talked about looking at the sign flags of X, which is our minuend, Y, which is our subtrahend, and D, which is our difference. So we have 8 possible ways to arrange the zeros and ones, and we basically ask, okay, does the sign of the difference make any sense? Because if it does not make any sense in these two cases, then that's when the overflow needs to be a 1. Okay, so that's what we talked about on Thursday. Do we have any questions about all that stuff? Oh, by the way, did we have a different subtractor when we are dealing with signed versus unsigned interpretation of the bit patterns? Or did we use the same subtraction mechanism? Same, exactly. We use exactly the same subtraction mechanism, whether the bit patterns are to be interpreted signed or not. So that's the nice thing about 2's complement, because that's what enables us to use the same circuitry for addition and subtraction, regardless of whether we want to interpret the patterns as signed or unsigned. Okay? All right. So we are going to move on. Unless you guys have questions about those topics, I'm going to move on. And just to remind you, it is also important to read the modules, at least keep up with the lectures. Okay? Now, if you can spare a little bit of time over the weekend, because we got 5 days between these two classes, and you go like, oh, I can just read a little bit ahead, okay? You even have a module, okay? That can be helpful. Even if you don't fully understand what a module is talking about at the pine needle level, if you just understand what the tree overall looks like, it's like, oh, he's going to talk about this, and it's important because of that, that's going to be useful already. Okay, so even if you cannot get down to the details and go like, I fully understand everything, but just understanding what we're going to talk about and why they're important is already very useful. So I strongly encourage everybody in this class to not only catch up with reading the modules, but also to read a little bit ahead of time. Okay? And interestingly, this is also what Windows does. Do you guys notice when you start up Windows, like after a reboot, your hard drive stays like constant on for a little bit of time? And do you know why that is the case? Yep, it's called prefetch, superfetch. That's it. Yep, which can be very annoying. So some people turn it off. My son turns off that feature. I don't know why that reminds me, why my earlier discussion reminds me of Windows. It just connects in my head. Did you guys see the connection? The prefetch mechanism of Windows, as opposed to reading ahead of time a little bit. Some of you do, and some of you don't. But that's okay. It's not going to be in the exams. Explain why tech thinks reading ahead of class relates to Windows prefetch, and prove it. And prove it. All right. So we are opening a new topic today. It's called floating point number representation. So the technical name of double, what you know as double in C and C++, is the IEEE double precision floating point number representation. I'll just call it double in this class, okay? So the nice thing about that notation is it can deal with a really wide range of values, okay? Now, there are 64-bit numbers, and that's why it's called a double, because it is double precision, which takes up 64 bits. So if you look at a 64-bit integer, that covers a pretty good range. But they're still integers, which means you cannot represent fractions, okay? And do we need to represent fractions in general in computers? Why would that be useful? Why do we need to represent things other than integers? What do you think your video game would look like if computers cannot handle real numbers? Yeah? Sorry.
Fractions allow for a level of precision that
Yep. So both for precision, but also for scales. Okay. So you can look at things from the really wide or outside perspective, but you can also zoom in to the details because it can represent all those values. I do have to remind you that there's a no food in classroom policy, so you can keep it in your bag, just not eat it because the faculty got hammered big time when somebody spilled coffee over the keyboard. So it's not just you, they come after us too. I suppose if you're the person who has to maintain the equipment in the room, you might get a little upset, if you find there's a puddle inside the keyboard, on the workstation. So anyway, so this is our topic. So before we get into the details, let's go ahead and see if we can make a few examples of things that I'm hoping you guys know already. So I'm going to use the tablet for this. And the tablet is actually getting a little bit easier to use now. I have a very low lag screencast mechanism now. So let's check this out whether it works well or not. I think it works better than last week. All right, so we'll start with a scientific notation that you may or may not know of, okay? I'm hoping you do, but we'll check. So we have 26 point, Oh, okay, so it works, right? So 26.371, and then lowercase e, and then we have a negative, 30 here, okay? So how many of you understand this notation? It's called a scientific notation. Okay, some of you do. And if you do not, that's okay. I can explain it. There are basically two portions to this number. Well, I will make it three. There's an implicit sign here. The implicit sign is a positive or non-negative unless you see a negative. Okay, so this number is by default a non-negative value. This part here is called the Mantissa, which typically you can use it, you can see this as the quantity, okay? This is the number of something. The number of what? This is called the exponent. Now, because we are dealing with base 10 numbers, so that means the value represented by this notation is 26.371 times 10 to the power of negative 30. In other words, the exponent is really controlling the magnitude of the value. Is that okay? Now this exponent, or this Mantissa, excuse me, this Mantissa is not normalized because it is a 26 point something. If it were normalized, it would be 2.6371, but then we have to adjust the exponent because if we divide the Mantissa by 10, then we have to add 1 to the power of 10. So the value can also be expressed normalized as this. 2.6371 times 10 to the power of negative 29, because when we divide 10 from the Mantissa, we have to remember to add 1 to the exponent of 10. So are we comfortable with this math so far? Okay, all in base 10, none of this stuff in base 2. Is that okay? All right, cool. And when do you use scientific notation? I mean, I'm pretty sure some of you have taken classes. Yep.
Usually in, like, what situations or what classes?
Well, either. I mean, you can give me examples.
You're trying to have a very precise value. You're trying to have a very precise value. You can use that. You would also mostly use it in calculus.
Okay. So whenever you have to express something that's not easily written without using the scientific notation. Yep, go ahead.
Say really, really big numbers and distances are really, really small.
Okay, so let's take a look at a few examples of those. I mean, we are probably familiar with those. Light speed. Okay, what is the speed of light? The speed of light is technically, 299,792,458 meters per second in vacuum, because if it's inside something non-vacuum, it does slow it down a little bit. But that's approximately what? 3 times 10 to the power of, let's check, 1, 2, 3, 4, 5, 6, 7, 8. So it's approximately 3 times 10 to the power of, what was it again? 8, okay. And if you type that on your calculator, 3 and then the EXP or the E button, depending on the brand, 8, that's a whole lot faster than typing 3 and then a whole bunch of zeros. Is that making any sense? So this notation is very, very handy. Let's look at the size of a transistor in the latest 8th generation Intel processors. Okay, so we'll look it up. Transistor size, Intel 8th generation. Okay, pretty sure we can find it it's a 40 nanometer technology. Okay, so if I want to express this in meters, okay, how would you write it? So how many zeros do we need to the right-hand side of a decimal point if you are to express it as meters? Go ahead. Yep. Okay, so that works. But the alternative of actually spelling it out is going to be a lot of zeros. 7 zeros. Yep, 7 zeros and then the 1 4. So you have to count, okay? So that's the problem is you have to count, what, 14 zeros. So if you miscount one, then the number is not of the right magnitude. So that's why scientific notation is so useful, because it separates the precision part, which is the Mantissa part, from the magnitude part, which is the exponent. Is that okay? And the nice thing, one thing that you might have noticed in our examples is we can use very few digits to describe quantities that otherwise would need a lot more digits. In the case of the speed of light, if I have to spell out in meters per second, I would have used up 9 digits, okay? Right? Because it's 299 and then blah 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 and then blah blah blah. Okay, there are 9 digits altogether. In the case of 14 nanometers, okay, well, in this, let's check out what is a nanometer. Okay, what is a nano? Okay, so we have point. 3 zeros would make it a milli. Okay, so this is milli. 3 more zeros makes it a micro. And then 3 more zeros would make it a, is it nano already at this point? Okay. So 14 nanometers is actually 14 here. So we need 9 digits to the right-hand side of the decimal point to express 14 nano, as opposed to 14 times 10 to the power of negative 9. Okay, so it's a very concise notation. Now, why do we want to look into concise notations? Because we want to pack things, right? We want to be able to represent a wide range of values, but without using a lot of bits. And that's why this notation, which we call scientific notation in base 10, is really helpful. So let's take a look at the scientific notation in general, regardless of the base. So with scientific notation, we have a mantissa, and then we have some kind of exponent. Let me back up a little bit here. Some kind of exponent that is relative to a particular base, okay? And the base to the power of e. So the only 2 portions that is explicitly stored is the mantissa and also the exponent. Those 2 components are explicitly stored into the representation. B itself is 10 if we are dealing with base 10 scientific notation. Okay, you see all the earlier examples. Those are all base 10 examples. So we specify the quantity, 1 4 or 14, and then we specify the magnitude, which in the case of a nano is 10 to the power of negative 9. So negative 9 becomes this E, B is 10, and then M is 14. In the case of the speed of light, it is going to be 3 as the mantissa, and then B is 10 because we're still dealing with base 10, and then E is going to be 8. Okay, but that's very concise. We don't have to write all of those zeros, which is kind of cool. It also allows us to deal with a wide range of values. Very, very small, not in terms of being on the negative side, but very small fraction of 1. And also we can express values that are really huge just by changing the exponent. Is that okay? So that's why we kind of like this representation. So now the question is, how can we use something like this in the computer using base 2? Well, I see no reason why this B cannot be 2. Okay? So let's go through a few examples and see what we can do or how we can convert a value into this representation, but in base 2. Is that okay? All right, so let's go ahead and give it a try. So I will try, let's say 65.125. And this is a base 10 number. This is a number that you know of. Okay, so we can rewrite this as 6.5125 times 10, okay, times 10 to the power of 1. That's the base 10 scientific notation, normalized with a normalized mantissa. A normalized mantissa simply means it has to be greater than 0, it has to be greater than 1, greater than or equal to 1, but less than the base itself. So in base 10, it has to be greater than or equal to 1. 6 is definitely greater than or equal to 1, but it also has to be less than 10. Well, I mean 6.5125 is definitely less than 10, so it's normalized. Is that okay? All right. But I'm not interested in base 10. I want to convert this into base 2. So let's see how we can convert this into a base 2, quote-unquote, scientific notation. All right. What do you think is going to be the first step to convert the quantity of 65.125 into a base 2 scientific notation? Change the base first. Okay, sounds like a good idea. So we'll do it step by step. We'll say that 65 is 61 plus 1 plus 0.125 because each component is a power of 2. Now, I can do this really quickly because I have done it many, many times, but some of you are probably starting to get the hang of it, right? You look at 65.125, you chop it up and go like, oh, okay, we can definitely see 64 as a power of 2. And then we got 1 left, which is also a power of 2. And then we got 0.125 left, which is an eighth, which is also a power of 2. So you can start to kind of pick out these pieces, a little bit more efficiently, the more you work with this kind of math. Okay, so, but this is still in base 10. We have to convert this into base 2 somehow. So we'll just rewrite 64 as 2 to the power of 6. 1 is 2 to the power of 0. And then 0.125 is 2 to the power of -3. Is that okay? So we are gradually converting into something that doesn't quite look like a base 10 number anymore. We are only re-expressing all of these as powers of 2. So what do you think 2 to the power of 6 should look like as a base 2 number? It is 1 of 2 to the power of 6, right? So the power controls the number of zeros in that base representation. So 64 is going to be 1 followed by 6 zeros. Very good. Okay, so 1, 2, 3, 4, 5, 6. Yeah, I can see that there's still a lag, between what I say and what you see on the screen, but it's much smaller than last week. Okay, what about 2 to the power of 0? Well, that's just 1 without any zeros. Okay, what about 2 to the power of -3? In other words, the equivalent question is, how do I express 10 to the power of -3 as a base 10 decimal number? .001, right? So that means, whatever number is here, you basically, this is 3, -3. You take that 3, you take away 1, becomes 2. That's the number of leading zeros before that 1. Okay? So it works out the same thing here in binary. So we have a binary point here. I don't want to call this a decimal point because we're not dealing with decimal, so we call it a binary point. So this place is telling us how many 2 to the power of -1s. Nope, we don't have any of that. This place is telling us how many 2 to the power of -2s. Got none of those. And this place is telling us how many 2 to the power of -3. We got one of those. Okay? So these are all in base 2. But we already know how to add base 2 numbers, don't we? Okay? And in this case, I'm adding 3 numbers at the same time, but since we do not seem to have any situation of carrying, it's pretty easy. So what do you think this number would look like? It's going to be 1 followed by 5 zeros. 1, 2, 3, 4, 5. A 1 here, 0.001 in base 2. So I have just re-expressed the quantity that we know of as 65.125 in base 10 into a binary number, which has its own, you know, digits to the left and digits to the right of the point. The point is really a convention. It tells you the mark where it separates, the quantity times whatever base to the power of 0 from, to the power of -1. That's the purpose of the point. Is that okay? Yep.
So for 2 to the 6th power,
Uh-huh.
I guess 7th bit is 1, but why wouldn't you have 1 less 0 and have the 6th bit be 1 because you have...
Well, let's see let's see if I can explain it this way. How many ones? 2, 4, 8, 16, 32, 64. So that's the other way to look at it, is to kind of count, and as you count, you spell out the powers of 2.
Okay.
Okay? Yep.
I don't understand how you can change that 125 to the 2 to the power of -2.
Okay, so let's do it step by step. From here to here, is that okay? No?
Yeah, this is the power.
Because 0.125 is also known as 1/8. 1 divided by 8.
Oh, okay.
Yep.
Oh, yeah, I got it.
Yep. It takes a little bit of familiarity of the powers of 2 seen as decimal numbers. Yep. All right. So you look at this number and go like, well, I could use this just as a Mantissa, but it doesn't seem very normalized to me. Does it look normalized to you, having a whole bunch of digits to the left of the point? Nah. Okay. So we're going to adjust that. All right. So let's see. Do I have space here? Yeah, I got some space. Can I do something stupid like this? Sure, doesn't really do anything helpful, but it's okay, because anything times 1 is, we get the same value back. Okay, that's fine. But then I can say, can I rewrite this as, okay, I have to be careful here. Okay, so do you see what I did? I just shifted the binary point 1 place to the left, okay? Which is basically saying I have just divided the Mantissa by not 10, by what? By 2. Very good. So the Mantissa is now half of what it used to be, but I want to maintain the same value, because otherwise I cannot use the equality symbol here. So what do I have to do to the exponent of 2 to adjust for that? Do I add 1 or do I subtract 1? I have to add 1, exactly, because I have to increase the power of 2 to compensate for the division of 2. Okay, do you guys see what I'm doing? The division that I did to the Mantissa has to be counteracted by increasing the exponent of 2, so that eventually these two are still expressing exactly the same value. Okay? Well, let's just work out the whole thing. Okay, I know it's going to be boring, but gives you time to ask questions and stuff like that. Okay, so this is, increase it one more time, and let's see. I mean, you guys can kind of know where I'm going here. 2, 3, 4, almost there. 3, 4. And now we are there. 1 point. 1, 2, 3, 4, 5. Okay. Do we have any questions about this derivation, other than it is really boring? We shift the binary point to the left by 1. We increase the power of 2 by 1. Wow. Okay. Cool. Yep.
So wouldn't the number of bits that you can be used to represent the number in floating point be more in this case than the number without?
Mm, Well, we'll get to that part later. Yep. Okay, but can someone tell me whether this makes sense or not? In other words, you look at the last final form, does it pass the quote-unquote sanity check? It's 1 point blah, 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 times 2 to the power of 6. Do you think that quantity is going to look like about 64-ish? Yeah, seems to make sense, right? Because if you look at this 1, that's 1 is multiplied by 64. And then we got some fractional terms, so it can be a little bit more than 64. So the sanity check passes, okay? Now, is it exactly 65.125? Well, you kind of have to do the check in more detail. But did I mess up the math when I shift the point to the left and adjusting the exponent? Probably not, okay? I might have miscopied a 0 or 1 somewhere. That can happen. But I did not make a mistake where it counts, which is, you just have to count the number of places you have to shift the binary point and add that much to the exponent of 2, and you have now normalized the base 2 number. Is that okay? All right? But we are not entirely done yet. We are really close, but not quite entirely done. So I'm going to extract this portion and copy, add a new page, and stick it here. There we go. So we're going to do, we need a little bit more because we have to kind of now say, well, but the exponent is not expressed as a base 2 number. So we have to re-express this as 5.001 in base 2. E is really just a separator to separate the mantissa from the exponent. The exponent is 6, which is 110 in base 2. Woohoo! So now we have a base 2 scientific notation. It works pretty much the same way as a base 10 scientific notation, except our base is 2 instead of 10. So do we have any questions about this? The last part. Okay, so in the original form, I said it's multiplied by 2 to the power of 6, which is not what the scientific notation is usually going to use. The scientific notation is going to use a lowercase e to separate the mantissa from the exponent. And we don't need the 2 here because it is understood this is a base 2 number, so we are using 2 as the base, right? So, but we do have to express the 6 as the exponent. But 6 is a base 10 number, and I want it to be a base 2 number, so I convert the 6 into a 110, because 110 in base 2 is the quantity of 6. So are we good so far? Okay. So we are pretty close to the IEEE standard of how floating point numbers are represented. Not exactly, but really, really close. Okay, so we'll get to that part later. So the next question is, if I give you a base 2 scientific notation, can you convert it back to the value that we normally use in base 10? Okay, so that's the next question. So I'll give you one, that's relatively easy, not long like this one. So we'll say, let's try 1.011, and then we'll make it, let's make it 2, so 10 in base 2, okay? So how do we convert this base 2 scientific notation back to the value that it is actually representing? What do you think the first thing is going to do? We're just basically following the steps, but backwards. Okay, so we identify the exponent first. The exponent is 10 in base 2, which we know of as 2 in base 10. Very good. So we're going to rewrite this as 1.011 in base 2. We don't touch the mantissa yet, but we then say times 2 to the power of 2. The base is 2 because it's the base 2 number, so this bigger 2 is because it's base 2. The smaller 2 is the exponent, which is 10 in base 2, is that 2. So we have to be careful, which 2 is coming, where each 2 is coming from. Okay, so that's cool. So in order to do the conversion, there are several ways to do it. Okay, you can convert the Mantissa part on its own. So the Mantissa part is basically 1, which is this one here, plus none of the halves, 1 of the quarters, and 1 of the eighths. Is that okay? 1.011 in base 2 has 1 of 1, the unit. It has 0 of the half, because 1/2 is 2 to the power of -1. It has 1 quarter, because this digit is controlling the quantity of 2 to the power of -2. And then we have 1/8, which, because it is 2 places or 3 places from the decimal point or binary point, so it is representing the number of eighths, or 2 to the power of -3s. So that's why this is how I convert the Mantissa in base 2 to something that we are much more familiar with. Well, I mean, they're fractions, but they're base 10 fractions. Are we good so far? Okay. And of course, we also know what 2 to the power 2 is. It is just 4. Okay. So now, I'm going to test your prowess of dealing with fractions. So what is 1 plus a quarter plus an eighth as a fraction? So if you use 8 as a common denominator, then you have 1 plus 2, which is 3. 3 plus 8 is 11. So you can see it as 11 divided by 8, okay? Or 11 over 8 times 4. And these two cancel out. So we get 11 divided by 2, which we also know as 5.5 in base 10. So that's going the opposite way. Okay, if I give you the base 2 representation, the base 2 scientific notation, this is how we convert it back to something that we are familiar with. Is that okay? Is this a lot harder than the base conversion stuff that we have done before? Or is it about the same? We're just dealing with one more thing, which is called the exponent. Kind of like that, right? Yeah. Okay, cool. So now, I think we are ready to go back to the notes. So the notes is actually a little bit more nasty, because the scientific notation, whoever came up with that, is trying to be as efficient as possible. So this is the actual scientific notation, quote-unquote scientific notation. It comes pretty close to what we already have seen, okay? So the salmon part, the salmon color, or the kind of pinkish color part, that's almost the Mantissa, okay? And I said almost because this is only the fraction of the normalized Mantissa. Because the normalized Mantissa in base 2 is always 1 point blah, 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 blah. So guess what? They say, we're not going to represent the 1 point. They're only representing everything to the right-hand side of the point. That's what the pink part is. The green part is the exponent. But, well, if it's the exponent, how do we represent negative exponents? You might think of, oh, we can use signed notation, right? The signed interpretation. So we look at these 11 bits as a signed integer. Well, for some really strange reasons, IEEE decided not to use that approach, and instead they use a bias. Okay? So you basically look at the green portion as an unsigned number, and then you subtract 1023 from it. The difference becomes the actual exponent in base 2. Don't ask me why they chose 10,023 and not 10,024, but that's what they did. The blue, little light blue portion is the sign bit. Okay, so you figure out the rest, and then the sign bit just says, okay, is it non-negative or is it a negative value? That's it. So it comes pretty close to what we have already discussed in this class, except you got a lot more digits in this case. So what you see here in the equation is really just a quote-unquote closed form of looking at the value represented by these 64 bits. They're alternatives to each other, but they work pretty much the same way. Let's look at the top one first. So the top one is looking at the sign bit. So this sign bit here, okay, the blue portion, is what we plug into SIGN, as a variable, okay. -1 to the power of 0 is 1. -1 to the power of 1 is -1. So that's how we change the sign of the actual value represented. And then this part here, this is one way to express it, is 1 point, okay? So they're using the constant 1 and then the point, and then the concatenation of bit 51, which is this guy here, all the way up to bit 0, and it's just copy and paste into here. Okay? So this is why I said the 1 point is implicit. It is not actually represented in a double precision floating point number. What about the exponent? If you look at the green portion as an unsigned 11-bit number, which we call E, then the actual power that you want to raise to 2 is E minus 1023. 1023 is called the bias. Once again, I do not know why they didn't choose 10,024 or 1024, which makes a lot more sense to me, and instead they chose 1023. But that's how it works out, okay? Okay, so given this representation, how do we confirm our understanding of a double precision floating point number format is correct? Well, let's do some conversions. Okay? And we'll start with things that are relatively easy, like things that we have done already. What about that 65.125? Sounds like an idea? Okay, so let's work with that one. Because we got most of it done already. It's just not entirely done, but it's pretty close. So we'll switch back to the tablet, and it's basically this number here. This is our 65.125. So we'll start with this. And let's see, how much space do I have here? We got plenty. Okay, so we'll just have to copy and paste it a little bit. Okay. So I copy this. And just kind of move it down here. Click. There we go. Okay. So we have to identify the 3 components, right? Which 3 components are we talking about? The sign, okay, that's the easiest one. What do you think the sign is in this case? The sign is a bit, which is a 0 or 1. It should be a 0 because the value we want to represent is not negative. Okay, sign is a 0. Cool. What about the exponent? The actual exponent. So the actual exponent is 6. But the green thing that we have to represent is biased by 1023. So what do we need to do? So E is 6 plus 1023, which turns out to be 1029, right? And we should express that in base 2. Oh, by the way, sign is a base 2 number. In other words, it's not 0. It is 0 in base 2. Wow. I'm just making a joke. Okay, what about 10,029? I mean 1,000. I keep saying 10,000. It's 1,029. What about 1,029 as a base 2 number? Remember, in your head, once you're familiar with powers of 2, you should be able to do the mental math and go like, oh, I see this power of 2, I see this power of 2, and I see that power of 2. So what is the one that really stands out and go like, yep, we got one of those? We start with the larger ones. 1,024. Okay? So we see 1,024. Then we got 5 left, right? 5 is pretty easy because 5 is 4 plus 1. So now I have chopped 1,029 into the 3 powers of 2 that it does contain. Okay? 1,024 is 2 to the power of 10. 4 is 2 to the power of 2. 1 is 2 to the power of 0. So that means E as a 11-bit number that is biased by 1023 is going to be 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus 1, 0, 0 plus 1. So that will give us 1, 2, 3, 4, 5, 6, 7, 1, 0, 1. Okay, let's count, make sure there are 11 bits here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Cool. Okay, so we got our 11-bit E, which is the green portion in Wikipedia. Is that okay? We got a sign bit, which is a 0. So what is left is really just the fractional part of the mantissa. Well, do we see it here? Where's my fractional part of the mantissa? Everything to the right of the point. So the fractional part of the mantissa is really just 0, 0, 0, 0, 0, 1, 0, 0, 1. Oh, we just ran out of digits. So how do we fill up 52 bits when we only got 3, 4, 5, 6, 7, 8, 9? When we only got 9 bits. What do you think is implicit to the right-hand side of the least significant bit here? They're all zeros, so we can always fill as many bits of 0 as we need in order to make it a 52-bit number. Okay, so I'll express that, okay? So the fractional part of the mantissa is just going to be this portion, and then we just pad zeros to the right-hand side of it. Is that okay? So let's string everything together. Let's do a concatenation and string everything together. So we got 0 for the sign bit. We got 1, 0, 0, 0. 1, 2, 3. Okay, I have to count here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then 1, 0, 1. That's our, this is our sign. This is our exponent. And then we got the fractional mantissa, which is 0, 0, 0, 0, 0, 1, 0, 0, 1. And we just pad a bunch of zeros after that to make it 52 digits. Okay. So this is the fractional part of the mantissa. I call it F. Okay. Are we doing okay so far with this? Yep.
I have a question. So where you say you write exponent equals 6, then it says E equals 6 plus 1023. Where
Yes.
does 1023?
It's the bias that is that's part of the standard.
Okay, there's a bias of 1002.
Yep. In other words, if E is 0, it's really expressing negative 1023 as the exponent of 2. Okay? But E is what we represent actually in those 11 bits. So are we still doing okay so far with this? A bunch of zeros and ones. Yep. Because this is how we express the actual value. The sign bit is this one here. So what happens when you raise negative 1 to the power of 0? That's one that we talked about that before, but I'm going to answer the question. What is negative 1 raised to the power of 0? No. What is anything raised to the power of 0? Well, except for 0 itself. Okay, anything raised to the power of 0 is 1. So this part becomes 1. The rest are non-negative. So that's why the sign bit controls the sign of the overall value represented in a double precision. Well, any floating point number. Okay, double precision is just the length of it. Yep.
So right there it says 2 to the E minus 1023.
Yep.
And on the when we were working through it, we
Yep.
added.
Right, because the expression E minus 1023 is the actual power of 2 that we need to deal with. So the 6 is E minus 1023, So in order to figure out what E is, we have to add 1023 to 6. That's how we figure out what E is supposed to be. And E is what we represent using the green portion as an unsigned 11-bit integer. So once again, I don't know exactly why they chose the bias to be 1023 because it just doesn't make sense to me. It doesn't click in my head. Yep.
So for the testing part, if we have not enough bit, we just fill up all zeros.
Correct.
High,
Yes.
up to 52.
Yes. So the more significant bits are these guys. Okay. So once you're done with these portions and you say, okay, I don't have any additional precision to provide, the rest can be all zeros because it's not going to impact the actual value of the mantissa when you pad additional zeros as less significant digits. Okay. So are we good so far? Okay. So let's switch back to the tablet. And we are looking at a pretty long number, 64 bits altogether. And we have to enter this into a program, into some place so that we can verify that this is actually working. I'm not going to enter like 64 zeros and ones because I'm going to make a mistake somewhere really, really fast. So what do you think I can do about this? It's like we have a whole bunch of digits to enter. And I don't want to convert it to base 10 because conversion from base 2 to base 10 involves a lot of multiplications, okay, and additions and stuff like that. So I'm going to convert this to hexadecimal. What do you think hexadecimal mean? Base 16. Why is it base 16? Hexa is 6, and then deci is 10. So hexadecimal is base 16. Okay? Base 16. But Tech, I thought you liked binary numbers. So why do you think base 16 has anything to do with base 2? What is 16 to 2? Exactly. So every 4 bits is 1 hexadecimal digit. Oh, that doesn't seem too hard, right? So how does the conversion work? So I'm going to use this space here to take a look at that. Okay. So we'll say, okay, let's just spell it out. 0, 0, 0, 0 is just 0. So the left-hand side is the binary representation. The right-hand side is the hexadecimal representation. So we got the usual stuff. Okay. Nothing too exciting. Okay. All right, so I'm going to stop here. Well, take a little break. 4, 5, 6, 7. Oops. Okay. So far we got 0 to 10. The next one, guess what? It's going to be 11, right? So it's going to be 1011, and then 1100, 1101, 1110, and then 1111. But in hexadecimal, we don't want to see it as 10, okay? Because 10 takes 2 digits, and in hexadecimal, 10 means 16, not what we know of as 10, okay? So that one doesn't work. So we don't like this. Get rid of it. So what are we going to do? Well, we're going to borrow letters from the alphabet. So we say, oh, this is going to be A, B, C, D, E, F. So that's how we deal with base 16 numbers, is we go from 0 to 9, just like a decimal number, and then we go from A to F so that we can represent the quantities of 10 through 15, but using only one single digit. Is that okay? Have you guys seen hexadecimal numbers when you deal with computer equipment? Yeah, so when do you use hexadecimal numbers? Memory addresses is one, yep, and what else? MAC address, exactly. or the ID of Bluetooth devices and whatnot, those are all expressed in hexadecimal because it's a very easy conversion between hexadecimal and binary. You basically look at the binary number in blocks of 4 bits. Each block becomes a hexadecimal digit, and it's just a table lookup. Okay, the more you use this table, the faster you can do the conversion without even looking it up. Yep.
Can you say one more time why we stop at 10? I mean, I know we want to keep it as a single digit from
Yeah.
0 to 9, but we could still represent 10 using only 4 bits, and same thing with 11.
Well, because we can't write it as 10 as in base 16, because 1 0 in base 16 has 0 of 1s and then 1 of 16. So 1 0 in base 16 means 16,
Okay.
and not what we know of as 10. So that means we have to use another representation for 10. And I know this is bad penmanship because my A looks like a 9. Okay, I can't stand that. So we're going to fix that. Okay. How about that? Now it looks like a 6, except it's the other way around. You can use uppercase. All right, so now let's see how we can convert this nasty 64-bit number into hexadecimal digits. Oh, how many digits are we going to have? It's a 64-bit number, so how many hexadecimal digits do we need? 16, very good. 64 divided by 4 is 16, okay, which is not too bad. All right, so we'll go ahead and do the same trick here. We'll do a copy and paste. Okay, it automatically pastes, which is nice. There we go. All right, so we'll go ahead and chop it into blocks of 4 bits. Now, the key to chop it into blocks of 4 bits is you're supposed to do it from the right and then work your way to the left. Okay? But in this case, because I know there are 64 bits, I can work it from the left as well. Okay? So this part you have to be really careful about. All right, so we group these 4 bits into one. Oops, I used the wrong tool. There we go. So we use these 4 as 1. That's 4 in hexadecimal. And then the next 4 would be these 4. That's a 0. The next 4 would be these 4. That's a 5. This is the next 4. That's a 0 again. And then we have these 4, which is another 4. And then we have these 4, which is 1 0 0 0. That's an 8. And then we have a bunch of zeros after that. So the hexadecimal representation of the bit pattern behind this 64-bit IEEE double precision floating point number is 405048, and then pad zeros until it has exactly 16 digits. Okay? So are there any questions about the conversion process up to this point? Yep.
So you're still looking at 4 bits in base 2, right?
We are not based in base 2 anymore. These are all in base 16.
Okay.
So yeah, go ahead.
Each 4-bit section,
Yep.
you're still reading it like the number below.
Mm-hmm.
That's the decimal.
Hexadecimal. So 4 is a hexadecimal digit. We just didn't have any pattern that would give us like A, B, C, D, E, F. It just didn't happen in this particular pattern. But potentially we can end up with like 1 1 1 1, then it becomes lowercase f or uppercase f. Okay? So if I were to spell this out entirely, okay? 0x is the prefix in C and C++ for hexadecimal. So if you say 0x and then a bunch of digits, it becomes a base 16 number. So it's 4050 48, okay? And then we have 10 zeros after that because we need to pad the whole thing to have exactly 16 digits. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That specifies the 16 the 64 bits to represent 65.125 as a double precision floating point number. Yes?
Why did they go 0x? Is that any significance, the 0 or
Um,
0x?
in C and C++, the 0 prefix, if you have 0 and then 25, 025 is actually an octal number. 0x means it's a hexadecimal number. So it's just a convention in C and C++. But it's also observed in most C-derived languages. So if you look at JavaScript, probably follows the same rule. Okay? Okay, so I give you this baloney that 65.125 represented as a IEEE double precision floating point number converted from binary into hexadecimal has this representation. Are you going to buy it? No, you shouldn't buy it. So then your question is, how do we check it? How do we check it in a way that it is not just tag reversing the explanation back to 65.125? Because it's likely that that's going to be self-consistent. So how do you do it?
We could just turn it back to the decimal by multiplying each of the numbers by.
Yep, you could do that. But that's going back to the issue that I had earlier, which is basically if I made a mistake in the assumptions, reversing the steps is going to use the same assumption, so it will still be wrong.
I was going to turn it into a decimal because I know that if I turn it into decimal, I'm comfortable with decimal. So if I turn the binary into hexadecimal to decimal.
Well, how about this? I'll give you a way to do this. So I'm going to write a very simple program, and it's going to include standard integer.h. If you have not learned about this concept, really should learn about it. Because this is what allows me to type something like this, uint64_t, which is guaranteed to be an unsigned integer type that has exactly 64-bit wide, okay? So I can actually control the width of my integer variable using this particular type. And this type def is in the .h file, standard integer.h. So if you don't know this already, this is a very useful concept that you should learn. So I put this as x here, and the main return 0. And I think I need to do something with x, so I'm going to say x gets x plus 1. X gets 7, and then x gets x plus 1. There we go. Because without these two lines, the compiler is too smart for its own good, and it will optimize the variable out of the entire program. Then I cannot use it. Okay. All right. So this program doesn't seem to have anything to do with what we are talking about, does it? No. Okay. So we compile the program. GCC-G means we want to include debug information. Then we can do warn all. Simple.c, and then we do a -o to simple. So my executable is also called simple. Okay, that's all. All right, no errors whatsoever. We now have an executable called simple. Run the program. Nothing happens, right? As you would expect from a program like that. Doesn't have any file input output. Doesn't do any actual computation. So what are we doing with this? Well, we're going to use GDB. This class used to be a lot more about GDB than it is now. GDB stands for the GNU debugger, and it is one of the best tools ever for debugging programs. How many people use a debugger in CISP360? Yes. Yay. How many people use standard in and standard out or C in C out to debug a program? It works, okay? But it's not as effective as using a debugger, okay? So if you use a debugger, set up breakpoints and stuff like that, not the focus of this class, but I'm just telling you, that's really a good way to debug programs. Okay, so in GDB, I can use L to list the source code. I put a breakpoint on line 9, and then I can run the program at full speed, like run, like so, okay? I can print x, it's going to be a 1, okay? It's going to be 8, yep, okay, because it's initialized to 8, and then we add 1 to it. So now it has a value of 8. No big deal, right? So far, nothing too exciting. So I'm going to do something now called set var, x equals to, what we saw a little bit earlier. So 0x 405048, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. Okay, doesn't complain. And if I print x again, it's like, whoa, what? How do we get that? Oh, that's a decimal number. What does it look like in hexadecimal? /x means print in hexadecimal. Ah, okay, we got it back. Wait, we're supposed to see 65.125, right? How am I gonna do that? Okay, so this is really a quick quiz on how much you remember from your C and C++ class. Okay, so I'll ask you this question. Okay, the print part is not the tricky part. X is an unsigned integer, and we know the value of x already, don't we? Okay. What is that? The address of x. Okay, and the address of x has a type of what? It is a pointer, but a pointer to what? It's a pointer to a 64-bit unsigned integer. Okay, not really surprising there. Okay, fine. And what can I do with an address? I can do it pointer arithmetics, but I'm not doing that now. How many people remember typecasting? And I can typecast a pointer. So instead of saying that this points to a 64-bit unsigned integer, I can now cast it to that. Now the asterisk is important because the asterisk means I'm casting the address of a 64-bit unsigned integer into the address of a double. In other words, okay, well, a pointer is a pointer. It's just a location in memory. Whatever type you cast it to doesn't really matter until you try to look at what is at that location, right? So what operator do I use to look at the content of an address? How do you dereference? Yes? The asterisk, very good. So if these concepts are starting to sound a little bit foreign to you, you might want to review C and C++, particularly the part about pointers and address of and types casting and stuff like that, because it is really important. Okay, so at this point, I have the expression that I want. Okay, so once again, let me explain what it means. We start with x, which is a local variable of the type 64-bit unsigned. Okay, we take the address of that. It becomes the address of a 64-bit unsigned integer. Then I cast the pointer. I'm not casting the content, I'm casting the pointer itself. So the pointer now becomes a pointer to a double, which also has the same number of bits as a 64-bit unsigned integer, but I'm going to look at it differently. So that's the last asterisk. Well, it's the last operation, but it appears as the first operator. The asterisk is dereferencing. In other words, okay, here is the address of a double. Look at the content, tell me what's there as a double. So I'm interpreting those 64 bits no longer as an unsigned integer, 64-bit unsigned integer, but this time I'm interpreting that as a 64-bit double precision floating point number. I'm interpreting bits differently now. Is that okay? Yep.
So the second asterisk is just a handy tool instead of having to put in like typecast, cast double.
Oh, this asterisk is really a part of the type that I need to cast it to. Okay, so let's press the enter key, and magically we got 65.125. Okay, and somebody's got, yeah, okay.
So that second time you printed out X,
Uh-huh.
what is that representation?
So print /x is saying, print in hexadecimal.
Right above it.
Above it?
Like
Oh, the $2?
yeah.
Okay, so that's printing x as a base 10 number.
Right.
So 4634 blah 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 blah, and the longer number is really the same thing as in hexadecimal 4050 blah blah blah. So the base 10 representation is like 3 digits longer compared to the base 16 representation.
But because it's not a double, that's why it appears
Because x itself has a type of unsigned integer. It is not a double.
Right.
But I'm coercing the interpretation of those memory locations as if it is a double by doing this trick. Okay, so some people are going to say, oh, but Tack, you're just, wasting time here because we could have done this instead. That's not going to work. This is not going to work because this is casting the value. In other words, it's saying, oh, look at x as a double. Well, x is an integer, okay, and you're casting it into a double. It's going to be pretty much the same value. You lose some precision, so you will not see this entire number. Instead, you will see a portion of that as the Mantissa, and then times 10 to the power of something, so that you to have the same number of digits. Okay, you're not going to believe me until I press the enter key. It lost some precision. You can see how in the original number we have 1440256, and it can only get up to the 3. It lost precision, and then it makes up for the quantity by exponent of 10, so we still end up with 18 digits, but we lost precision in the process. Okay? All right. So the whole process works, okay? Your lab today is about the understanding of exponents, doing this type of conversion, back and forth either way, and figuring out, what is the power that I need to compensate for moving the decimal point, how many places to the left or to the right. So it's really, just kind of making sure that you really understand the mechanism of the double precision floating point number format. Do we have any questions up to this point? Okay, what about the other way around? If I start with a hexadecimal representation like this, convert it back into the base 10 representation. Well, let's see. With this one, if I just want to add, if I want to double the quantity, okay? This was 65.125. If I want twice of that quantity, how do I nudge the hexadecimal representation so that the value represented is twice as big? Increase the exponent by 1, right? Do I need to take into consideration there's a bias of 1023? No, because the bias is already there. It's already built into it. So I just really have to identify which digit is responsible for the unit of the exponent. So does anyone remember the length or the width of the exponent? How many bits does it take up? 11, okay? But the sign bit takes up 1 bit, so that means the most significant 12 bits is of interest to me. Okay? So how many digits are we talking about in hexadecimal? 12 bits would be 3 hexadecimal digits. So that means 405 in the hexadecimal representation would include the sign, which is non-negative in this case, and the 405 really is responsible to specify the exponent. So if I change that 405 to 406, the quantity represented should be doubled, because I would have just increased the exponent by 1, right? So let's see if that works. So I'm just nudging the number, so I have to go back to the setvar command here. Instead of 405, I now make it 406, okay? And then I go back and reinterpret the content at that location as a double. This time we should get 130.25, because that's twice of 65.125. Okay. Well, let's see if that works. Ta-da! It does work. So this is the sort of thing that you kind of have to experiment, to kind of go like, okay, so how do I nudge it in this direction? How do I nudge it in the other direction? Make very small, minute changes, okay, just so that you can get a sense of, oh, okay, so this is how I can get it to change in this way, and so on. Yes? Change the 4 to a C, then it becomes the negative version of this number. Very good. Okay, so let's do that. So the idea is to change the 4 to a C. Now, what is the difference between a 4 and a C? C represents 12. 4 represents, well, 4. 12 minus 4 is 8. So what is so significant about 8 in a hexadecimal digit? 8 is the most significant bit of a 4-bit chunk in a hexadecimal digit. Because when you have 4 digits or 4 bits, you have 1, 2, 4, 8. So the 8 is responsible for the most significant bit of a hexadecimal digit. So that means, yeah, go ahead.
That just doesn't mean you're changing the sign.
Exactly. Exactly. So by changing the 4 into a C, I'm adding the most significant bit of 1 to the most significant bit of the entire 64-bit number. And that turns out to be the sign bit. So I'm switching the sign bit from 0 to 1. So that means the quantity now represented is going to be a negative quantity, but the same absolute value. Okay? So we should get negative 130.25 now when I reinterpret it. That's exactly what it was. So this is the kind of exercise that you can actually do and experiment when you use this approach. If you don't like this approach, you can look into the concept of union in C and C++. I'm pretty sure that concept is not discussed in 360. Am I right? Did anyone learn about the concept of a union in CISP 360? Nope, it's not. A union is related to a struct, but it's actually quote unquote the opposite of a struct. Okay, so short of that, this is the best way to kind of experiment with the underlying representation. Is that okay? Now you can flip this the other way around too, because I still got 3 minutes to go, so you're not going to get shortchanged, not ever in my class. So you can reverse this whole thing, and you can say set var, okay? But when you do this set var, do it like this. Okay, so we extract the address of x, we cast it as a double pointer, and then we dereference it. In other words, we're doing exactly the opposite. I am storing a double, okay, if you want to emphasize, okay, what shall I use? Like 3.14, okay. So in this way, I'm actually storing the double precision format of 3.14, the value of 3.14, into x, which is basically our unsigned 64-bit integer. So now if I print x, what do you think we should get back? It's a pretty huge number, right? If I print it in hexadecimal, I'm expecting it to be 0x4 something, okay? Because the exponent of 2 is still a pretty small number. Okay? Yep.
Right next to the dollar sign 8, that you're saying that that's a base 10 number?
This is a base 10 number. Yep. So $8 is showing you the unsigned base 10 interpretation of the 64-bit unsigned integer. So if you look at those 64 bits and say, I want to look at this as a 64-bit unsigned integer, that's the base 10 representation of that value. Okay? But if I use the same trick again and interpret the content at the same location, but this time I interpret those 64 bits as a double precision floating point number, I should get 3.14 back. And that's, well, close enough. This is why, you know, there are things, there are values that cannot be represented exactly in a double precision floating point number. Just like in base 10, given a fixed number of digits in base 10, can you represent 1 divided by 3? Nope, because the 3 is recurring. It would take an infinite number of digits in base 10 to represent exactly, you know, 1 divided by 3. And base 2 has situations like that as well. So that's why when I reinterpret the stored value, it's off by a little bit because I ran out of precision to store the exact value. Is that okay? So these are neat little tricks that you can learn in GDB. It's great for this class, but GDB itself is also great for many of your other classes. All right. It is 10:20, so I'll let you guys take a break, and then I'll meet up with you guys at the lab. And I know you guys know this already, but I'm just going to say it anyway. By the time you get